Hey everybody, welcome back to physics. Hope everyone's doing well. Today we're going to be talking about the refraction of light. We learned about refraction a bit when we were talking about waves in general. So we know light bends when it goes from one medium to another because light could exhibit wave-like properties. But because light bends going from one medium to another medium, we can end up with some pretty cool effects in our physical reality, and we can actually use this idea of refraction to our advantage, building things like eyeglasses and lenses. Take a look at some of these pictures before I go to the next slides. I'm sure you've seen this phenomenon before. You stick a straw in a glass and then you look and you're like, hey, my straw's all messed up here. We learned that straws don't make their own light. They're illuminated, which means they reflect the light. So there's some light source, the light reflects off the straw, and when the light heads to our eyes, it doesn't really bend through air, but it will bend through glass and water, creating these distorted images. Here's a cool physics teacher in the pool. Physics is fun. I used to hate this play on words when I was in physics. I cringed hard, but now I'm a physics teacher, so I guess I have to enjoy it. Take a look at this image over here. This is pretty cool. So we have a spoon in a glass of something. I'm actually not sure if this is water or maybe some kind of oil. But what's really cool about this effect, you get a lensing effect. You start seeing the yellow on this side of the glass and the blue on this side of the glass. And then we even see some reflection, like we talked about last lesson in the image, underneath here on the table. Here's a pretty cool application of refraction as well. I said that light bends, creating these distorted images, but here you could actually truly see a light ray bending. That's the great thing about lasers. Lasers we could kind of model as a light ray. So the laser comes in, and then it bends when it reaches this new material, and then it bends again when it reaches back to the air. Notice how these two are parallel. We're in the same medium of air, but it bends here through this medium of glass or whatever that brick is made out of. And over here is one that's really cool as well. I don't know if you guys are aware, but behind this glass is the Sydney Opera House. And the Opera House, when we look at it through this glass of water, we get another lensing effect. We can see the Opera House upright up here, and we see it inverted down there. These images getting inverted, magnified, shrunk, distorted, this all has to do with refraction in this case. So let's review refraction real quick. I froze again. So as you recall, when we talked about waves in general, one of the phenomena that waves exhibit is this idea of refraction, bending from one medium to another medium. Waves bend as they pass from one medium to another. Refraction is the change in direction of a wave moving obliquely from one medium to another due to a change in the speed of the wave. So take a look at this diagram here. We talk about this word incident. That means it's the incoming ray of the wave. That's the direction of wave propagation. We reach the boundary, and then the wave bends. That means that we're moving in a slower medium down here. Waves move faster up here, slower down here. And this change in speed of the wave is the reason why that the wave bends. Now remember some of the things we talked about. The speed of the wave changes, the wavelength changes, but the frequency of the wave remains the same. Frequency only depends on the source of the wave. What we're going to be doing this lesson is really looking at refraction closely in terms of light, and we're actually going to quantify how much the light bends going from one material to another, and how much that speed changes if we know something about each one of these materials. Okay, so I want to teach you a tool that we're going to use to help us better understand and predict how these waves bend the way they do. And this tool is called the index of refraction. What the index of refraction is, it's actually a ratio. We take the speed of light in a vacuum, which we denote as c. You can find that on your reference table, page 1. 3.0 times 10 to the 8th meters per second. That's always the speed of light in a vacuum. And we divide it by how fast the light actually moves through that material. We know that light slows down through certain materials, but let's say it slows down from 3.0 times 10 to the 8 to 2.0 times 10 to the 8. We can take that ratio And then the index of refraction for that case that I just made up would be 1.5. And we could use this index, we use this ratio, then we have the tool of the index of refraction to help us identify the type of material and then use this number to help us in our mathematics that we'll see in a little bit. So if something is going the same speed, like if we're trying to find the index of refraction of the vacuum, we're going to get an index of refraction of 1, which means that the wave is not slowing down at all. But if it slows down a whole bunch and this number gets very, very small, then the index of refraction is going to get very, very high. Again, the index of refraction is just a tool that we made up. It's this ratio of speeds that help us identify and work with the types of materials that we're using and help us better predict how the wave is going to bend going from one medium to another. Okay. So what scientists can do is they could figure out how fast the light is going in these different materials and then tabulate the index of refraction for a whole bunch of different materials: air, water, corn oil, diamond. And then we can keep track of all these different indices of refraction, and we can use them to help us make mathematical predictions in the future for different things. Okay. So before we use this equation, there's some observations I want to make about this equation. Again, the index of refraction is unitless because we're taking two speeds, meters per second divided by meters per second. This is a unitless quantity. It has to do with the material that the light is moving through. The index of refraction can never, ever be smaller than 1. 1 will be the lowest index of refraction based on the definition, because the fastest that light can travel is at the speed of light, c. So if we put the fastest speed here, right, as we increase the denominator, we'll decrease the index of refraction. But the fastest speed here that we could put in is c, and c divided by c would be 1. So you'll never see an index of refraction lower than 1. If you're doing calculations and you end up with an index of refraction less than 1, go back, check your work, because that can't be the case. Okay, so the greater the index of refraction, the slower light moves through the material. Water has an index of refraction of 1.33. Again, as we increase this number, the speed of light through that material is decreasing. Diamond has an index of refraction of 2.42. Light moves slower in diamond than it does through water. Okay, now you might be asking, Mr. Hatzfeld, what's the deal with this index of refraction? Why are we making up this tool to help us figure out how much light is bending? Well, I'm glad you asked. Even though I know you're probably not asking, I'm just putting questions in your mouth. But the reason why we use this index of refraction, as we're going to see in the future, is we can use it to mathematically predict how much the wave will bend in a new medium. I'm going to hold off on this for now. But first, I just want to talk about the indices of refraction for a bunch of different types of material. So here's the absolute indices of refraction for a set frequency. Through air, the index of refraction is essentially 1. Now, I said that the index of refraction for a vacuum would be 1, but if we take this out to way more significant digits, we will start to see it's like 1.000, and then we start seeing digits, but we could estimate that to just be 1. Corn oil is 1.47. Diamond is 2.42. If you look through this entire list, you'll see that diamond is the highest index of refraction, thus light moves the slowest through that material, which is actually important for why diamonds are so sparkly. The light actually gets trapped in there. Now, the fact that I'm showing you this table, this is on page 2 of the reference table, by the way, this means that you will be expected to know where to find this table and know where to find these indices of refraction to make calculations in the future. A question could ask, light goes from water to crown glass. So you have to look and say, okay, well, water has an index of refraction of 1.33. Crown glass has an index of refraction of 1.52. You have to know where to find these numbers to use them for our questions. All right, so before we dive into the mathematics, let's talk about what light does at these boundaries one more time. We talked about what waves do at boundaries, but let's imagine it with light for a second. So we have an incident ray, and we have two different mediums here. This is a boundary because we're going from one medium to another. The incident ray comes in, strikes the boundary. Now we know that energy cannot be created or destroyed. It only changes form. And we know that waves transport energy from one place to another. So what happens to this light energy when it strikes the boundary? Well, we just talked about refraction. Some of that energy is bent, and the wave that's refracted will bend and move into the new medium. But that's not where all of the energy goes. Some of the light gets reflected, bounces off the surface, which we talked about in the last lesson. And some of the energy actually gets absorbed by the material. I said it before in a previous lesson, but that absorption of energy could cause things to heat up. Like when you wear a black shirt outside, the light comes in, gets absorbed by the black shirt because black materials are the best absorbers of light energy. And that shirt will heat up, makes you hot in the summertime. White shirts reflect the most light and keeps us a little bit cooler. Okay, but here we're focused on this refraction of light, the bending of light. So how can we calculate exactly how much it bends by? We know the law of reflection says that the incoming angle is equal to the outgoing angle. But I can clearly see that these angles, measured relative to the normal, are different. So how could we predict exactly how much the light is going to bend? And for that, we're going to look at Snell's law. Okay, so what Snell's law is a mathematical relationship that's relating the indices of refraction of the material and the incident angle and the refracted angle. Snell's law is succinctly stated right here. N1 sine theta 1 is equal to N2 sine theta 2. Equalities in physics are powerful. When we have an equality, that means we can mathematically manipulate it and predict what's going on with the angles or the indices of refraction if those are unknowns. So going back to our last image here, we can say that this is N1, like this is the first material where the light is incoming. Here's N2 where the light is being refracted. This would be theta 1, which is the incident angle, and theta 2 is the refracted angle. Okay, and that is all organized right here. So on the left side is where I like to put the incoming light rays, right? What is the index of refraction of the light where it's coming in, and what angle is it coming in at? That's where we plug in for N1 and theta 1. Is it coming from air? We plug in 1.0. Is it coming from water? We plug in 1.33. If it's coming from a vacuum, we plug in 1.0. And what angle is it coming in at? 10 degrees, 20 degrees, 30 degrees, measured relative to the normal. And on this side, this is where the light gets refracted. Here's the new material, N2. Again, is it diamond, 2.42? Is it water, 1.33? That's what we plug in here for the index of refraction. And theta 2 is the refracted angle. Again, angles are measured relative to the normal line. All right, so make sure in front of you, you have your reference table, you have pencils and paper, you have a calculator. We're going to be doing some math in this lesson. And as always, I want you to try this math before the video continues on and I just give you the answer. It's very important that we know how to work these things out on our own. Okay, so what do you think? You guys ready for some examples or what? I think I'm ready. Here is Snell's law, example 1. Base your answers to the following questions on the diagram on the right. And we want to know some things about this situation. Well, we have air, glass, and it exits the glass back into air. So we're going to only focus on the interaction between one of these boundaries. Yes, there's two refraction events occurring, but we could kind of just focus here for now. We'll be looking at that area there. Our goal is to find the index of refraction of the glass, the speed of light in the glass, the frequency of the light within the glass, and the wavelength of the light within the glass. Now, a lot of you guys might be looking at this question and say, hey, I remember seeing glass on our reference table. Let me just run and grab the index of refraction of that glass. But the thing is, if we look back at our table, it didn't tell us what type of glass we have. And it only gives us two different types here, crown glass and flint glass. So we can't assume that it's one of these types of glass. We're going to have to do some calculations to figure it out. There it is. So the index of refraction of the glass. What can we use here? Well, looking at the diagram, I see that the light is incoming at 60 degrees relative to the normal, and the refracted angle is 34 degrees relative to the normal, 34.5 degrees. We know the index of refraction of air, because that is given on the reference table, and there's only really one type of air that you guys need to worry about. So don't we have enough information using Snell's law to figure it out? I think we do. Well, we can start with the equation. N1 sine theta 1 is equal to N2 sine theta 2. That's Snell's law. And we can use this to figure out angles, but if we have enough information, we can also use to find indices of refraction. So on the left side of the equation is the incoming light. The right side of the equation is the refracted light, the outgoing light. So let's look at air. I know the index of refraction of air is 1.00, and the incoming angle is 60 degrees. I also know, I don't know N2, but we do know the angle at which it's being refracted. That's 34.5 degrees. Cool. So with this equation, we have one unknown, and we can absolutely solve for it. So plug this into your calculator and make sure you know how to do it. 1 times sine of 60 divided by sine of 34.5. That's going to be, I'm not a math wizard, I did it before I had you guys on. The index of refraction is 1.53. Boom. So the light is going to slow down in the glass. We actually know that off the bat because the light bends towards the normal line. And we learned previously that when the wave bends towards the normal line, that means it's going slower in this material. And the higher index of refraction compared to where we started tells us that it's going slower. So that's a good thing. By the way, Snell's law is named after a dude with the name of Willibrord Snellius. You can look him up. That's a real guy. We shorten it to Snell because we're real tight, me and Snell. All right, part B. We want to know the speed of light inside of the glass. Well, I know the speed of light in a vacuum, but I don't know the speed of light inside of the glass. Can we find it with maybe another equation that we learned this lesson? What's the definition of the index of refraction? We learned, this is also in your reference table, by the way, the index of refraction, N, is equal to C, the speed of light in a vacuum, divided by V, the speed of light within that material. Well, we just solved for N. We know C from the reference table. We can solve for V. Let's plug it in. 1.53. Isn't this nice? We're doing math again. It's been a little while, huh? 3.0 times 10 to the 8 meters per second divided by V. How fast is the light moving in the material? That's V there. So let's solve for V. It's going to end up being 3.0 times 10 to the 8 divided by 1.53, multiplying it by like 2/3. The correct answer is going to be 1.96 times 10 to the 8 meters per second. Boom. Okay, and as you can see, this is slower than the speed of light in a vacuum. So the light goes from the air to the glass, slows down, it bends towards normal, and we have how fast exactly that light is moving through the material. 1.96 times 10 to the 8th meters per second. Now, this is kind of amazing when you think about it. By using this tool of Snell's law, we can start putting numbers behind this idea of refraction, and we could bend light exactly how much we want to if we know something about the material, the shape of the material. This is exactly how eyeglasses are made. We use Snell's law to make eyeglasses. Depending on if you're nearsighted or farsighted, we send light through the lenses, we bend them in just the right way, and we can make those images less fuzzy to you, make them nice and clear using Snell's law. All right, we're not done with this question just yet. We're going to, where's my eraser? We're going to do C and D. Make sure you have this down, pause the video, and I'm going to erase. Okay. Definitely destroyed my TV over this quarantine. That's right. Physics is more important than TVs. All right, part C. So if the incident wave has a frequency, get out of the way, of 7 times 10 to the 14th hertz, what is the frequency of the refracted wave? Oh. Well, if you remember the beginning of the video, we did talk about frequency when we were discussing the review of refraction. Frequency only depends on the source of the wave. Frequency will not change every time it's refracted, which is really important. I'll talk about it in a second. So if the frequency is the same, let's write down the answer first. Then the frequency is going to be what was given here. Probably don't need to write 0.0, but that's okay. Times 10 to the 14th hertz. It's the same. Refraction does not change the frequency. And that's very, very important because I talked about those eyeglasses before. Imagine that when you look through your eyeglasses, that the colors of everything changed because the frequency of light is directly related to what color of light we're looking through. So imagine if it was refracted and then things start changing colors. We wouldn't have good eyeglasses then. But because the frequency stays the same, then the color of light is going to stay the same. So it's the same frequency, 7.0 times 10 to the 14th hertz. Okay, and finally, part D. What is the wavelength of the refracted wave? So the speed of the wave changes, the wavelength of the wave changes, but the frequency stays the same. Wait, frequency, speed, wavelength? That's a familiar equation, isn't it? Remember, just because we did this equation lessons ago doesn't mean it goes away. It still applies to waves in all these cases. Always keep these tools in your toolbox. So we know the wavelength, we want the wavelength, we know the frequency, and we know the speed. Let's calculate this out. So the speed from our previous part was 1.96 because we want the refracted wave, so we want to know how fast it's going in the material. 1.96 times 10 to the 8th meters per second is equal to the frequency, which we know is 7 times 10 to the 14th hertz. Remember, hertz is cycles per second, so it's 1 over seconds. And then we want lambda. All right, so 1.6 times 10 to the 8th divided by 7 times 10 to the 14th. Lambda, oh, it's a weird lambda. I guess that'll do. Is going to be equal to 2.8. Make sure you can do this on your own too. Times 10 to the -7th meters. Wavelength is measured in meters, how long the wave is. And there we go. We have all parts of this question done. We use Snell's law, we use the definition of index of refraction to figure out speed, and then we used an old school equation to figure out wavelength. All right. I hope everyone's doing okay so far. I'm going to erase. Boom. Let's do one more example before I let you go. Okay. So take a look here. They give us a diagram. Water, medium X. Light comes in at a 45-degree angle, gets refracted at a 29-degree angle. And our goal is to find the identity of medium X using the information in the diagram. Oh boy, so what is medium X? That's what the identity means. Is it diamond? Is it air? What is it? Well, just looking at the diagram, I see that it bends towards the normal line, so I know that it has to be going slower in this material. So we know the index of refraction has to be greater than water, right? Because the higher the index of refraction, the slower the light's going to be moving. But that still doesn't help me find exactly what medium X is. But we do know the index of refraction of water. We can look that up in the reference table. We know the incident angle, we know the refracted angle. Can't we solve for the index of refraction of medium X? And if we know that number, isn't there a table that we could use for reference to figure out what that number corresponds to for the material? Let's do it. All right, so we're looking at Snell's law that we learned today. N1 sine theta 1 is equal to N2 sine theta 2. All right, let's plug in what we know. Going to the reference table, you can see that the index of refraction of water is 1.33. Sine theta 1 is given to be 45 degrees. Sine of 45 degrees is square root of 2 over 2. You don't have to know that though. At least not in this class. You probably might have to know for math. We want to solve for N2. Sine, and then theta 2 is 29 degrees. All right, we have one equation, one unknown. We can definitely solve for this. N2, plug it into your calculator. Make sure you can do it. But N2, I get to be 1.93. Now, if you box that and say, I'm done, submit to Canvas, that's incorrect because that's not what the question asked us. The question didn't ask us what the index of refraction is. They asked what the identity of medium X is. You have to use this information, take one more step, go to your reference table, take a look, let's see what material has an index of refraction of 1.93. Oh boy, there we go. So we're looking for a 1.93 on our reference table. The closest I see is down here, 1.92. Doesn't match perfectly, but that could have to do with significant digits and things like that. But because this would be the closest, we can definitively say that the identity of the material is something called zircon. And yes, that is a real material. It's not an alien name. Okay. All right, and that's all the examples I have for you today. Some questions might be asking you to solve for an angle. Notice that the questions I asked today were solving for the index of refraction. But let's say I had a situation where we knew N2 sine theta 2. Let's say we knew this index of refraction, this angle, and we wanted the refracted angle. Keep in mind that we would have to use the inverse sine function to take theta out of the sine function. Okay, you know what I mean? Like if I wanted to algebraically solve for theta 2, just doing some quick algebra real quick. Quick algebra quick. Right? But if I want theta 2 on its own, if I want to know exactly what angle it is, then you have to make sure you take the arc sine, the inverse sine of whatever this is. Okay, so don't forget about that second sine function in order to solve for that angle. All right, so we're going to try some examples using Snell's law and some of the things about refraction that we learned today. Brushing off those calculators, getting some math done. I hope everyone's doing well, and I'll see you in the next video.